It is indeed a great pleasure to be here. Let me show you a picture. It's a group of miners ready to go down, or maybe a group of constructors, construction workers ready to go up. So let's see, where did they go? And there is an extra person there, somehow envying those who can have a helmet. And there they go to the site. So it's going up. And of course, Yuval is there. And I had the pleasure to teach him a course. Of course, he was the best, but Avi has not taught a course to my son, but which is a pity. But he did teach him how to do this kind of acrobatic production up between the trees. So it was an excursion in Hungary. So in a way, that's something I would never have been able to teach my son, because I don't think I would like to go up there and hang there. So.
There was nothing about teaching, you just have to overcome the fear.
Okay, well, that's maybe itself. Okay, so let's turn to easier stuff, and in fact talk about what is generic. And let's start with a very easy example of bipartite matching. So a perfect matching, we look at a bipartite graph which has same number of nodes on both sides, and then we are interested in whether it has a perfect matching. And here is the usual adjacency matrix. It's the non-symmetric adjacency matrix, bi-adjacent matrix of this graph. And it's easy to see that a perfect matching corresponds to a non-zero expansion term. We have already seen this in Shafi's talk, I think, yesterday. And it means that if there is no perfect matching, then the determinant is necessarily zero. But the determinant could be zero even if there is a perfect matching, because of cancellations. And there's this trick which often, I think, Edmonds, it's attributed to Edmonds, or he did this. It's called the Edmonds matrix. And it's, the idea is that we replace the ones by certain variables here. Or in fact, I would like to think of these variables as numbers, but they are not rational. In fact, they are algebraically independent transcendental numbers. And if you look at then the determinant is zero if and only if there is no perfect matching, since there cannot be possibly any cancellation between expansion terms. Now, you might think that it's much preferable to think of these as variables, because you get a polynomial and you just have to check whether the polynomial is identically zero. But and the third way of thinking about it is that they can be random substitutions, and so random substitution would also work with probability 1, if say, and then of course you cannot do really real numbers choose randomly, but if the underlying set you choose from are sufficiently large, then you get a correct answer with high probability. Non-bipartite matching is similar. This was in Todd's paper where he actually proved the matching theorem. That he also talked about this matrix, which is a version of the adjacency matrix, except now, since it's non-bipartite, every edge of the adjacency matrix is represented by, oops, oh my. should switch off the. You always should switch off the wireless. Okay. So there are now two entries, and one is an xij, and the other one is the negative of xij. So it's a skew-symmetric matrix, and perfect matching, again, gives you a non-zero expansion term. And you have to be a bit more careful with cancellations, because, of course, there are no cancellations, but Tott proved that the determinant of this matrix is 0 if and only if there is no perfect matching. And as far as I know, there is no derivation of Tott's condition, the combinatorial condition, from this condition. Whereas in the bipartite case, there is a nice derivation of the Koenig-Hall condition from this algebraic form. So I just wanted to mention this. And random substitution, of course, again leads to a randomized algorithm. Now let's go on, and now let's come to a more interesting and maybe a bit surprising fact. It's also an old fact along these same lines. We look at an arbitrary graph, and we take 3 points. Instead of 3, we could have any k here, but my pictures are for the case k equals 3. We fix these, the vertices in A to a triangle, and then we replace the edges by appropriate high-tech rubber bands, which shrink to 0 if allowed, and which don't get tangled. And then we let it find its equilibrium. And so we get this rubber band representation of the graph. Now, there's a lot interesting to say about this. If you compute the energy, theCij's are constants which correspond to the strengths of the edges. They don't necessarily have to have the same strengths, these rubber bands. And then the energy is represented as such a sum. And if you differentiate, you get that the equilibrium which is reached. I mean, it's easy to prove that it has a unique equilibrium once the graph is connected. And the equilibrium is, and at the equilibrium, each point is sort of a convex combination of its neighbors. So every node sits in the convex hull of its neighbors. Now, this is you can prove various interesting facts about this representation. What I would like to quote now is a result we had with Avi and Nati, which says that if the edge strengths are algebraically independent, then this representation will be in general position for every triple if and only if G is 3 connected. So the general position means that no 3 of the points will be on a line. Maybe here is the this is the showing the necessity of this condition, that if there is a cut set of size 2 and you nail down 3 points which are on one side of this cut set, then the other side will collapse onto the segment connecting these two cut points, so that it will not be general position. The converse takes a bit longer argument. What I would like to point out here, that actually there are two non-degeneracy concepts here. One is this algebraically independent edge strengths, which means that the edge lengths don't satisfy any algebraic, or the edge strengths don't satisfy any algebraic condition which is not identically true, which is not an identity, and the general position. And I will sort of have a stroll through some combinatorics and show you other interesting examples where these two non-degeneracy notions pop up. But before that, let me mention, actually, this is already an interesting problem. It includes most of these generic algebraically independent substitution problems. You have a linear space of matrices, so you fix the size n by n, say, and you take a linear space of matrices, and the generic rank of this linear space is the maximum rank of any matrix in this space. Now, it is not, you could also be interested in the minimum rank. You would get a much more difficult and much more interesting problem. This way, this is obviously randomized, computable by a randomized algorithm, because if you pick some kind of smooth distribution on this subspace and you pick a matrix from it, then of course with high probability, this will, probability 1 actually, this will have attained the maximum rank here. But we are interested in actually computing this. So this matrix has generic rank 3, but this matrix has generic rank 2 because every skew-symmetric matrix of odd size has 0 determinant. I mean, this is a linear space of matrices if you vary U, V, and W, so it's linear space. Now, I assume that the space is given by generators, so we know explicitly a family of finite family of matrices, and we'll look at all linear combinations of them. And again, as I already mentioned, if you substitute random values for the xi's, you get a trivial randomized algorithm. Now, here is what we know about this. What I know, maybe there are other. I know 3 sort of classes of examples where the generic rank has a good characterization and can be computed in polynomial time. One is if the subspace is generated by rank 1 matrices. The other one is where the subspace is generated by skew-symmetric rank 2 matrices. And the third one is sort of, sounds first similar, but it's a different construction. Again, you take a family of skew-symmetric matrices of rank 2, but now you don't take linear combinations of them, but you take a vector and you apply these matrices to this vector to get the columns of a matrix in your space. So this is case 3. If you know any other general cases when this generic rank problem can be solved, I would be very interested. These have been known for 30 years, and I haven't seen any progress. By the way, the first one is really matroid intersection in the linear case. The second one is equivalent to matroid matching. Again, linear case, but matroid matching is only solvable in the linear case. And the third one, we'll meet it. It's related to planar rigidity. Okay. So this is a question. So let me introduce a notion. So take a graph and take some d, dimension d, and let us assign to every node of the graph a vector in R to the d. A unit vector, say, with the condition that if 2 nodes are non-adjacent, then the corresponding vectors should be orthogonal. Here are some examples of how to do such an assignment. For example, here you can assign the same vector to all these 3 nodes, so that could be one of the basis vectors, because they are mutually adjacent, so there is no condition in here. Whereas for a pentagon, you need dimension 3 if you want to do a similar construction, because you can only assign the same vector to 2 of them. And here is another assignment of such vectors in dimension 3. Now there are a lot you can ask about orthogonal representations, and I will not go into it, but let me just put an additional condition of general position. So when can you assign, find an orthogonal representation in D space such that any D vectors are linearly independent? And it's an old theorem we have with Mike Sachs and Lex Schreiber that graph G has such an orthogonal representation if and only if it is n minus D connected. This is somewhat related to the result I mentioned with Avi and Nati, but they don't imply each other. It's sort of a similar flavor. But of course, this difference, the dimension here is D, and here it's n minus D connected. So the question is, okay. Now, let me say one word or two words, a few words about how this is proved, how this representation, general position representation is constructed. That's the interesting direction. If the graph is sufficiently connected, you can construct such a representation. So let me say a few words about how this is constructed, because there's some interesting twist to it. So start with any vector labeling, u1, un, and let's define new vectors, f1, fn, recursively, where each fj is the sort of the component of uj, which is orthogonal to all those previously defined vectors. It has to be orthogonal to, so those which are non-adjacent to the current node. So this is, we call this the G-orthogonalization of the original U, and it generalizes Gram-Schmidt. If G has no edges, then this is just a Gram-Schmidt orthogonalization. And so I actually thank Robert Weismantel for this observation that this is really can be considered as a generalization of the Gram-Schmidt procedure. Now this depends on the ordering of V, which is the hard core of the proof to show that it depends, but it doesn't depend too much. Now, the point is that if the main theorem is that if G is n minus D connected, and you choose the original labeling at random, then the G orthogonalization will be in general position with probability 1. Now, these are non-zero vectors because a zero vector is never in general position. So it follows that you can scale them to length 1. So you get an appropriate representation here. Now, I found this idea of generalizing Gram-Schmidt orthogonalization this way, and just put it as a general question of finding or other applications or other properties of this generalized Gram-Schmidt procedure. Okay, let's go to another area, not quite unrelated, which is bar and joint frameworks. So the point is now that instead of rubber bands, we put rigid bars for the edges. So the points are somewhere. In this case, they are supposed to be in the plane, but can also work in higher dimensions. And so we look at this structure that we obtain this way. Now, the joints are flexible, so the angles between these rods couldn't be anything. Now, there are various, so we are basically interested in what happens. Is it rigid? Does it have motions? And so on. And we can see that already the same graph realizes various different ways of asking this question about how rigid this is. So, for example, if you look at this structure, this turns out to be locally rigid. There is no way, if you try to wiggle each node so that each edge maintains its length, then the only way to do it is to rigidly move the whole plane. But it does have a global motion. You can flip this black vertex to the outside. On the other hand, if you look at the degenerate situation when the black node is on the line of the two nodes at the bottom, then this does not have any global motion, so it is rigid. However, you feel that there is something here. You can almost wiggle this up and down, and in fact, it has a special property that if you move this up or down by epsilon, then it stretches the edges only by order epsilon squared. And so we call this that it has an infinitesimal motion. In first order, it preserves the edge length. Let me show you a couple of more examples. This guy has a finite motion. If we fix the dark nodes, then this white triangle can circle around the fixed part. But if the same graph is drawn like this, then it's rigid. It's not obvious, but it can be proved. And in the third situation, which is the symmetric way of drawing it, it has an infinitesimal motion, because if you rotate this triangle by epsilon, then these three edges are only stretched by order epsilon squared. So it has an infinitesimal motion. Okay, so here is some algebra that goes with this setup. I denote by Lij the length of the edge ij, and this is considered to be fixed. And so this is the basic equation here. Or you can differentiate this equation. You imagine that ui's are moving in time, and then you get an equation like this. And these are the velocities of the points, and these are the positions of the points. And the crucial thing is that this kind of infinitesimal motion is equivalent to having a non-trivial solution to this system of equations. And we also can observe that the number of equations is equal to the number of edges, and the number of unknowns is 2n if we are in 2 dimensions. And so it has and also notice that it must have at least 3-dimensional solution space, because the 2 translations and 1 rotation give a 3-dimensional family of rigid motions that also provide solutions to this. We can these are sort of semi-trivial solutions. So if we look at linear dependence between these equations, so how many of them are these are equations for the unknowns ui dot, then such a relation is a linear dependence. Now, one way to read this is that Sij is a scalar, just the multiplier for one of these equations. And for every node, the coefficient of ui dot must vanish, which gives this equation. So we sum ui minus uj times this Sij, and it must give 0, which means that if you think of this as a stress, then this stress times the vector along the edge gives you the force with which these bars act on node I, and if it's in equilibrium, then it must be 0. So this is called a stress, such an assignment of Sij. So we know that there is a stress if and only if these equations are not independent. Now, there is an old theorem of Asimov and Roth, which says that the entries of if the entries of the positions are algebraically independent, that's this sort of generic position, then every infinitesimal motion extends to a finite motion. So indeed, it was no coincidence that when we had the black dot between two white dots, it was a degenerate situation when we had to illustrate a special infinitesimal motion. Now, in 2 dimensions, the problem is solved, and it's again a classical theorem of Laman, which says that a graph is stress-free in generic position. First of all, it doesn't depend on which generic position you put it in. So what generic, that means algebraically independent coordinates. It doesn't matter where. So if it's stress-free in one or in all generic positions, if and only if every set of x spans at most twice the coordinate of x minus 3 edges. No similar characterization is known in higher dimensions, so it's a big open problem. And this actually follows from this generic rank of a matrix space, the third case. So it's somehow it's a general position, genericity condition, which translates into a matrix space and leads to the third condition there. And it's a nice combinatorial condition that it is rigid in a generic position. We can think of it as infinitesimally rigid, or by the previous theorem, it means it has a finite, it does not have a finite motion. If and only if adding any new edge, the graph will contain 2 edge disjoint spanning trees. So it's a nice combinatorial way of characterizing rigidity in 2 dimensions. Now, there is another possibility of defining generic where the edge lengths are algebraically independent, not the node positions. And there is a theorem which says that the edge lengths are algebraically independent, implies that the framework has no strengths. Now, this is really implicit in the work of a number of authors. That's why I put it in parentheses. And the proof is quite interesting. It uses some ideas that I have not seen used in other parts of combinatorics or computer science. So maybe it's because it's my ignorance, but nevertheless, let me show it to you, the idea of the proof. So for every collection of node positions, this is a d times n variables or unknowns here, all the coordinates of the positions, and we are in d dimensions. Now, I assign the vector of edge lengths. Actually, I squared them just to make it sure it's just actually simple algebraic expressions of the original edge lengths. Let's denote this by lambda u. Now let's look at those u's where those positions where there is a stress. It's not, so that means that it's not hard to see that there is a stress is equivalent to saying that the Jacobian of this map is 0. It's basically how we got the equations by differentiating the corresponding equations. And so what it means is that the set of those positions where there is a stress is a real algebraic variety over the rationals, because that's just equation with rational coefficients. That actually may be one or more equations, because the Jacobian may not be a square matrix, but then there are more than one equations. Now, there is a Tarski-Seidenberg's theorem which implies that the image is also a semi-algebraic variety. this semi-algebraic variety means that it's the finite union of sets, each of which can be defined either by algebraic equations or by strict algebraic inequalities. Now, okay, so far so good. Now, in our special case, when the edge lengths are algebraically independent, then it means that this lambda u has algebraically independent coordinates. It means that these coordinates cannot satisfy any equation. So this means it's only strict algebraic inequalities that it has to satisfy, which means that a small neighborhood of it also satisfies exactly these. So it's actually an interior point of the image. But there is another theorem in differential geometry, Sart's theorem, which means that the image of these kind of singular points always has measure 0, and this is a contradiction. I think it's a very nice proof, which probably should be remembered. Now, let me speak a little bit about the configuration space of a framework. This is a classical one from 19th century, where if you fix the two black points, then it's called an inverter. This point A moves on a circle, and the point C is always its inverse with respect to the circle on which B and D move, and therefore it moves on a straight line. And this was a big problem for mechanics to construct such a thing that leads this point C along a straight line. Actually, you would think that the configuration space here is just this segment on which C can move, but actually not, because if C reaches the end, then B and D coincide and they can switch places. So altogether, the configuration space is a circle. But there are it need not be always a manifold. So if you take a parallelogram and you look at its configuration space, then it turns out that there are really two ways to get between the two degenerate situations, one with convex and one with concave quadrilaterals, and so the configuration space is different. On the other hand, if you take a generic quadrilateral, then the configuration space is a circle. And there is this theorem, which is not hard to prove from the previous one, that if the edge lengths are algebraically independent, then the configuration space is a manifold. So this degeneracy with the parallelogram occurred because the parallelogram is not, the edge lengths are not algebraically independent. And also, it's also true, it's in another related theorem, that if the node positions are algebraically independent, then the configuration space is also a manifold. And this was proved by Hendrickson and Jackson and Kivash. And the previous is just sort of a digest of their proof. So let's look at, so these were structures which were in generic position. Now we are interested in structures which are simply in general position. That means that we don't want points to be on a lower dimensional space than they would necessarily have to be. And this comes up nicely in the context of global rigidity. So a bar and joint structure is globally rigid if every realization with the same edge length is congruent to it. We have already seen an example at the beginning of not globally rigid. So this configuration is not globally rigid in the plane because we can flip one of the triangles to the other. But if we put in an extra bar, then of course it becomes globally rigid. Now, global rigidity is another very interesting subject. I wanted to show you two more examples. This is a cube drawn in the plane. If you draw it in sort of generic position, then it turns out it's not globally rigid. You can count it has a local motion. On the other hand, this special drawing of the cube is globally rigid. So unlike in the case of infinitesimal rigidity, when the worst case was when you put them in generic position, or best, depending on which case, for globally rigid, special positions will be globally rigid. Sorry? Sorry? This one? The right one is globally rigid. It's not generic. This is not generic. There are parallel. I mean, it's what you think. So there are two rectangles and so on. So this is globally rigid, but not generic. This is generic, but not globally rigid. And of course, triviality is that every connected graph has a globally rigid realization in every dimension because you just put all the points in the same position. But this is, of course, cheating, and so you want to have, you must impose some kind of non-degeneracy condition, and general position is a nice one. We cannot go much beyond general position, so for its generic, it would not work. And there's a nice recent theorem by Alpha-Kich which says that G has a realization as a globally rigid bar and joint structure in general position in RD, if and only if it is D plus 1 connected. The proof uses the theorem about orthogonal representations in general positions I mentioned earlier, but you should notice that it's a non-trivial way of using it, because here we are talking about D space and D plus 1 connectivity, and there we have D space and n minus D connectivity. So there is some dualization involved. Actually, it uses a Gale dual construction, but let me not go into the details. I may have 2 more minutes. No, I have 7 more minutes. Yeah. Okay, so let's go on. So I would like to conclude with 2 slightly different notions of genericity. One is transversality, also sometimes called the strong Arnold property. If you have a family of surfaces, then we say that they intersect transversally at a point x if the normal vectors at that point x are linearly independent. So we assume here that they are smooth surfaces. So it's something like that. So locally, it looks like it's a very clean intersection. No touching. And algebraically, it means that here are the equations which define the surfaces, and then the gradients of these equations are linearly independent. So this is some kind of nice or non-degeneracy property. And let's see what it gives us for, say, bar and joint structures. Well, suppose that they intersect transversally. It happens if and only if, well, it means that the gradients are not linearly dependent. So if they don't intersect transversally, then the gradients are linearly dependent. And if you write, and we have looked already at this condition, And that actually gives the stresses.
What is the surface here?
Oh, the surface is defined by, a surface is in n times d dimension, defined by this equation, this algebraic equation. So you take the gradients and you look at linear dependence between the gradients, and we have seen this is just stress. So this condition gives stress freeness, which is very important property in engineering, of course, and just in the study of these structures. Now, you can also look at orthogonal representations, and I will not give a precise definition here. Colin de Verdière, in fact, he was it who introduced this transversality condition in combinatorics, and he defined two parameters. One is, well, you look at the minimum dimension where a transversal, and you have to also assume it's faithful, meaning that the inner product of two vectors which are adjacent is non-zero. Faithful orthogonal representation exists, call it eta g. Actually, no, you subtract it from n, so you need the gain in the trivial dimension n. How much? What is the minimum? Sorry, yeah, okay. And mu g is defined similarly, except now, if you want to say it quickly, you have to look orthogonal representation in Minkowski space. So space where the inner product is plus 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 relative to a matrix which has one negative eigenvalue. And again, there is some faithfulness condition. Inner product of two adjacent points should give a negative value. Now, there's an interesting theory for both of these, and all I would like to mention is, first of all, that this transversality condition implies the extremely important property that both of these are minor monotone. It's a non-trivial property, but it can be derived from the transversality. And I just to sort of illustrate what is interesting combinatorially, and sorry, this should be, I'm sorry, I have the wrong Greek letters here. So eta of g is closely tied to tree width. It's always an upper bound of tree widths on the tree widths of the graph, but it can be bounded by some maybe the fifth power of the tree widths or something like that from the other side. And this second one, where I put eta here, but it should be mu, is less than or equal to 3 if g is planar. So that was the first result of Colin de Verdière that really showed it that this is a very deep way of looking at it. So this transversality, I have shown you 3 examples where this kind of transversality plays an important role and leads to very interesting combinatorial things. And of course, as already I have done a few times, I would like to see more examples and just would like to call your attention to this. And finally, in my last minute or so, I would like to mention that you can ask genericity in a quantitative way. So generic means, or maybe general position means that the determinant of any d is non-zero, but how far from zero it has to be. And there is, here is, I just show you quickly one example. I don't know if there are more though. You look at a finite metric space, and you look at a random subset of size k. Actually, I should have written here 2 to the k, because you only want to have powers of 2 maybe. And then you assign to each node I the vector consisting of its distances from these random subsets. It's denoted by x of u. So this way you you embed the metric space into a linear space.
So x of u is x of I?
X of I, thank you. And there is a famous theorem of Bourgain which says that for all nodes u and v, the distance is their distance in the metric space. If you look at the expectation of this, of their L1 distance of these two points, of the two assigned points, then in expectation, this is up to this m is log n, so up to a logarithmic factor, essentially the same as the original distance. And if you don't like that it's only about the expectation, then you can repeat this in many coordinates, and then you will get just by high concentration results, you can get that with high probability this holds for all u and v. Now this has many applications, among others the Layton-Rao approximate Max-Flow-Minkowitz theorem. There's this beautiful paper by Linnell, London, and Rabinovich where they explore this connection about the Max-Flow-Minkowitz theorem, approximate Max-Flow-Minkowitz theorem. But I would like to just mention that the other application of this construction, or a variant of this construction, on approximate bandwidths, that basically, if you choose the parameters right and you project the points on a random line, then this gives an ordering which is approximately good for bandwidths. And this is a beautiful paper of Uri Feige, and that's which I consider as the beginning of quantitative genericity. Because the key observation is that this Bourgain representation is actually volume respecting. So with high probability, again, you have to choose the parameters right, but for sets of size about the logarithm of n, of the whole size, if you take any k points, then the determinant of the image, or this is the volume of the convex hull of the image, if you wish. I'm very imprecise here, not writing out factorials and so on, is bounded by, now here is the funny thing, what is this volume in the metric space of the original point? So what does it mean? You have k points in the metric space. What does it mean, their volume? And that's what Uri introduced. What you can do is you pick a minimum spanning tree on these points, an optimum spanning tree, and you take the product of the edge lengths of this spanning tree. And this is what we can think of as the volume in a metric space, and then you can prove that it's this kind of volume is respected. And then this inequality, the lower bound here is the crucial step in the proof that in the design of this approximate bandwidth algorithm. So I would like to again put here a challenge about, can this be taken further? So how would a quantitatively generic orthogonal representation or other things look like? What can we say about that? Judging from Uri's paper, it will not be an easy task, but nevertheless, I think it's an interesting question. And so, happy birthday, Arnold.